Hello, everyone, and welcome back. Can you believe it is chapter 8, our final chapter of calculus? And you've done great all year long, just a little bit more, and then you will be done with this class. So, what is this chapter about? This chapter is going to be talking about volume, and this lesson is talking about volumes by slicing. Now, if we're in person, we would be doing a lab for this, but we are not. Not everyone, and it's not quite the same in this environment. So I'm going to demonstrate the lab for you, especially to help with number one, because this is a very valuable lab to help visualize this technique to calculate the volume of shapes. So if you don't want to use my information and say you want to do it yourself, do it with a friend, do it with a family member, it's pretty fun. And here's what you would be doing. So if you want to do it yourself for this lab, the goal is to find the volume of some sort of fruit or vegetable. So raid your fridge, find a fruit or vegetable that your mom or dad don't need, and you can do this lab. Now, what you'll need to do this lab, the materials needed, is you will need, of course, a fruit or vegetable. You will need a knife, of course, to cut it, which I'll show you in a second. And then you'll need some sort of measuring device, a ruler, measuring tape, something that will help there. And then a calculator will probably help too to calculate it. Okay. So if you want to do it yourself, you can. If not, you can just follow along with my demonstration lab and use my data to help answer number one. All right. So I'm going to demonstrate the lab so you can use the data for number one. So what I have here is, I know the problem talks about a lime, but I do not have a lime in my fridge at the moment. So I have an orange. There is a orange. And how are we going to calculate the volume of this orange, right? So what we're going to do is we're going to slice it, and I'm going to turn it sideways, and we're going to make cross sections of it, okay? So hopefully I do this right, because I don't really want to cut a second orange. And it is a Cara orange. If you're wondering what, if you're like, oh, my eyes messed up or my screen messed up, that is pink. It's a Cara orange that we have. Okay. So I'm going to cut this orange up into these cross sections. Okay. And there you go. So there's some cross sections, and I'll take one away to study it. Look at those later. Okay. Put that orange there for me to eat. Now, take a look at this cross section of this orange. And my question to you is, what shape is it, right? So if I just push this down a little bit so I can have my paper, I could have predicted that. Let me fold this a few times so it doesn't continue to get the paper. There you go. Okay. So there is the cross section of an orange. And if I asked you, what shape is this cross section? And you might be thinking that it is a circle. In fact, you see a circle. But you have to consider the entire cross section. So it is not a circle, because a circle is 2D. And what I created is a cross section that is 3D. It has a width, right? This is 3D. So what is it with a width that's circular, and then it's more or less circular all the way down to its base? Well, this very much resembles a cylinder, where you can see from an aerial view, it would look something like this, where you have your aerial view of the orange, it's circular, and it more or less follows the same dimensions down to its base. Good. So it is a cylinder that we'd have, and it has a set width, and I'll measure that for all of them so you can do this lab. Well, yeah, number one's just about the lab, so let me measure them for you, okay? So if we wanted to find the volume of the entire orange, you would need to find the volume of every cross section. Now, what is the volume of a cylinder, by the way? The volume of a cylinder is, because a cylinder is the same, it's a circle at every measurement going down words. So it's the area of the base, pi r squared, for the circle times the height, because every circle h many times. Okay. Now for this lab, let me sketch these for you. Let me measure these for you so you can do the lab. All right. So let's do cross section. And then I'll give you I'm going to measure the diameter or the width of every cross section and then the diameter of every cross section. That should help you calculate the volume for number one. Okay. So here we go. So we look at cross section number one, and this is all approximate. And I wish, we could be doing this. And I am using centimeters, by the way. All right. So the diameter of this approximately is 6 centimeters. So cross section number one has a diameter of 6, and this is all in centimeters, by the way. And the width approximately is 1. That'll be an easy one to calculate. So there is cross section number one. Second cross section to help you calculate the volume of this is roughly 7 point, I'll just do 7.5 to keep it easy for you. And the width of this cross section, I was trying to keep them good. So let's see if I was able, a little bit less. Unfortunately, I didn't do as good. So that's about 0.75 is the width of that one. Okay. My next cross section here has a diameter of 7 3/4. Cross section 3, and it has a width of about 0.75 again. At least I was getting consistent. My fourth cross section, I didn't cut it perfectly. Just rip that carefully. There we go. Okay. This one has a diameter of 8 and the width of 1. This next one don't want to do it in inches, stay consistent, is 7.5 with a width of, that one looks like 1. Yeah, that's a width of 1. And then my very last cross section for your data to calculate the volume of my Cara orange is 6.5 with a width of approximately 1 again. Okay. So that'll be the data you need to calculate the volume and estimated volume of my orange. Okay. On my wet paper. So so your job for number one is what's the estimated volume of my orange? And the big things that you'll need, and hopefully this helped you visualize, and if not, do it yourself, is that each cross section is a cylinder, not because it's 3D, all right? Has a width to it. And the volume of a cylinder is pi r squared h, where I gave you the diameter of every cross section, and then h, I guess I could have called this, instead of width, height. But I'm sure you could figure that out. Okay. Now, let me do one more example to help you understand this a little bit. And this one resembles one of the problems you would have seen, that you will see later in it. Is say we have, earlier today, I wanted to find the volume of a pear. So this wasn't my first time cutting fruit up today. I actually did it earlier this morning. I cut the pear into 5 cross sections. I was a little bit more accurate this time, where I did them 2 centimeters apart exactly, not the 1 and 0.75. Come on, Mr. Hein. But I cut the pear into 5 cross sections, 2 centimeters apart, measure diameter of each, estimate the volume of each pear. All right. So we want to find the volume of this pear. We just need to find the volume of every cross section. So this very bottom one, again, we're going to estimate that it creates a cylinder-like shape. All right. So that very first one, that first cylinder, if I have it out here to help you visualize this, It's not perfect, that's what an estimation. Well, the height is 2 centimeters, and the radius would be 3.5. Or actually, I'll just write it as 7 over 2. Okay? So the first volume is going to be pi times 7 over 2 squared, pi r squared times h times 2, plus my second cross section, which if I draw this one on the left side, would have looked something like that, where the radius would be 9 over 2, and the height was also 2. So then the next volume would be pi times the radius squared times the height of 2, plus my next volume would have been pi. Again, we're creating cylinder-like shapes here. The radius of this one would have been also 7 over 2 with a height of 2. And then we have 2 more, pi times, and I'm not going to draw pictures anymore. I think you can visualize that. And then the last one, the last cross section, there would be pi plus 4 over 2 squared times 2. And there's the volume with my 5 cross sections as cylinders. Okay. Now, going through it, I could, I guess, pull out the 2 pi because that's in every single one of them. So I could write it as this 2 pi and write it as 7 over 2 squared plus 9 over 2 squared plus 7 over 2 squared plus 5 over 2 squared plus 4 over 2 squared. All right, and then let's see if I can calculate this out. So 7 over 2 would be 49 over 2 plus 81 over 2 plus 49 over 2 plus over 2 over 4. These are all over 4. 25 over 4 plus 16 over 4. Adding all that up, 49 plus 81. I'll use my calculator for this one. 49 plus 81 plus 49 plus 25 plus 16 is 220 over 4. That would go to 2, and 2 and 220 would go to 110. So my estimated volume here is going to be 110 pi centimeters cubed. And there's an estimate of the volume of that pair using this method of cross sections of cylinders. Not even as cylinders. I take cross sections and they naturally become cylinders. Now, what if I wanted a better estimate? What if I wanted a better estimate? What would I do? Well, if you want a better estimate, it'd be better if I cut them into, if I cut more cross sections, which would then have which would imply, what's the right word there? A smaller thickness of each cross section. Because if I can cut that down, each cross section, into a smaller and smaller one, then it's more likely that that's an exact cylinder at that moment. In fact, the thickness, if I could get them so tiny, it would be such a tiny cylinder of a small width, an infinitesimally small width. All right, infinitesimally small width. Maybe I call that dx. Or in this case, we're calling it height. Maybe I call it dh. Infinitesimally small height. And then I can get the radius. Now that wouldn't quite be a cylinder because it'd be so tiny, and I know it's hard to see. That actually would be called a cylindrical disc. And again, it's only because it's so small that it's not quite a cylinder. But it follows the same properties, it just has a special name. All right? And if you add all those up, what would you have? Well, you would add all those up. And how do you add up infinitely small things? Well, you use the integral, which, by the way, I don't know if I ever showed this to everyone. The integral is actually an S sign. It's like an S. And why is it an S? Because it stands for summation, right? Integrals are the idea of adding up a lot of stuff. So it's, I don't know if I said this here, squiggly line, but it's actually an S, where it would be the sum of the volume of every cross section, the volume of each cross section. But you'll see in the next video where that comes to be in the formula that we're going to use to calculate the volume, the exact volume. Okay. So there it is for lesson 1. hope that makes a little bit of sense, and hopefully you can tackle that first one. I guess I'll go enjoy my Cara orange now before it gets too dry. If you do have questions, stop by office hours, talk to each other, and I'm here if you need me. All right, bye-bye.